Hello everybody, Adam Lusick here, and today we're going to be breaking down what exactly Retrieval Augmented Generation is. I realize that on this channel I've covered a lot of different advanced RAG techniques, but never actually took the time to do the basics, so that's what this video is going to be dedicated to. So what we're going to do is intuitively break down the entire Retrieval Augmented Generation pipeline as it applies to different language model-based systems, and show practically what's happening at each step along the way. So at the end of this, you should have a pretty decent understanding of what's actually going on behind the scenes of Retrieval Augmented Generation applications. So to start with a simple definition, RAG or Retrieval Augmented Generation can be understood as essentially providing the most relevant, up-to-date information alongside any sort of question or query that's being sent to a language model to get an accurate answer or action back from that language model, generally based on the information. At a high level, a flow of information through a language model with and without RAG can be thought of kind of as this. Without a RAG system, the user input or whatever input you have gets sent directly to the large language model, and then the large language model generates its final response out. On the contrary, what's happening with RAG is as you send an input to the language model, that input is also used to retrieve any sort of relevant context, documents, or information that you might have related to that input, and then both the input and that relevant context are both sent to the language model, which then conditions it on its final response generation. So you're probably wondering, why is this important? So language models have a lot of intrinsic knowledge and ability and understanding of the world around them, but they don't necessarily have the most up-to-date or readily available domain-specific knowledge. If we look at something like GPT-4o, we can see that it was trained with information up to October 1st, 2023. So any events, information, releases, or anything that happened after October 1st, 2023 was not included in its training data. On top of that, the very nature of a language model itself comes into play here. It is not in a language model's purview to actually regurgitate facts or spit out kind of exactly what it has learned, rather learn what language is and how language kind of, encompasses the entire understanding of the world to generate novel text. And while it leads to incredibly capable and knowledgeable systems, these language models do not have access to the up-to-date domain-specific or proprietary information that might be most useful to us. So RAG systems try to fill in this gap by building on top of the language model's already incredible intrinsic knowledge by providing the right context at the right time. And with this, we're able to have a separate system that has all of the relevant, up-to-date, niche-specific, esoteric information that we might want to provide as context and make it available to the language model so that it can use that at runtime to provide its final responses. So this generally leads to a lot more accuracy or contextual understanding of the task at hand when using these language models in very specific situations. And by specific, I generally mean, for your own domain-specific information, rather than the more generalized assistance that we see with things like ChatGPT or Claude or Gemini. So let's take a little bit of a look at this actually in action before we break it down even further. So to see how a language model handles very domain-specific questions, both with and without RAG, I have set up a specific scenario. I am going to ask a language model questions about the Bosch particulate matter sensor. And this is a good example for a few reasons. It's very niche and specific. I don't even really know what the hell this thing does. Plus, it has a lot of super esoteric niche technical specs that you can see in something like a data sheet here. I don't even know how you would interpret something like this. Plus, on top of this, this was also released in 2025. So the language model itself should have no actual understanding that this even exists as a product in the world. So if I take a question of interest, what is the maximum power consumption of the BMV 080 in continuous measurement mode, and I run it just straight through a language model without any RAG framework, what we will see is that it says the power consumption of the BMV 080 in continuous measurement mode is 1.3 milliamps. Now, if we run this through a retrieval augmented generation flow that has a lot of the knowledge of the BMV 080 loaded into it, we will see that our response back is the maximum power consumption of the BMV 080 in continuous measurement mode is 181.9 milliwatts. So a very different answer, 1.3 milliamps versus 181.9 milliwatts. Which one is right? Well, looking at our specific documentation, we can see that in continuous mode, our power consumption is 181.9 milliwatts. So our RAG response wins. Perfect. So with that higher level understanding of what RAG does and an example of how we can get some accurate answers on niche specific data, which I'm sure you can start to think of your own use cases after seeing something like that, let's go through actually setting this up. And the first step is actually to create what is known as a knowledge base. And your knowledge base is essentially going to be all of the relevant domain-specific knowledge that you want to be able to use and provide as context to the language model for whatever queries you're using. Generally, these are set up and specific to the application. So let's say I wanted to make an AI chatbot for the BMV 080. What I would want in my knowledge base is product documentation about that specific product. But overall, a lot of what this is just going to be your entire collection of whatever unstructured data you want to use to provide as context for whatever questions or actions you want your language model to be able to follow or respond to. What we mean when we refer to data as unstructured data is essentially everything that's not stored in like a table-based database. So some of the examples that I have here are things like PowerPoints, Word documents, emails, Excel files, images, audio recordings, and all of those things that aren't specific, tuples or rows of individual data that you might see in a traditional relational database. But it's not as easy as just tossing all those files into a language model. Language models themselves tend to process, mostly with an asterisk there, text. Behind the scenes, language models actually mostly process things called tokens. And what these tokens are essentially just conversions of words or pieces of words and phrases into numbers. Of course, the language model itself is one big kind of math equation, or it can be thought of as a math equation. So we need some way of converting everything into those numbers. That process is called tokenization. You can see a quick example of what tokenization kind of looks like in these two pictures here. So all of these words become split up by the individual color regions here, and then those are converted into the numbers. Then these numbers are actually what's being processed through the language model, and the language model does spit back out numbers or tokens that look like this, which are then mapped back towards words so that we can actually read them. But the big idea there is most language models tend to process text. So we still need to do some sort of preparation of our data after first identifying our candidate data set into a text-based format. Now, as I just hinted at, a lot of the more modern language models are introducing multimodal inputs, so you can input not just text, but video, audio, images, and others as direct inputs. You can see here that some models like Gemini 2.5 Pro support all of these different modalities. But for the most part, we're going to be wanting to deal with text. So we're going to focus on text for the remainder of these examples, but do know that a few different systems and RAG systems also support different modalities. But just for now, we'll cover how the main use case of text actually works. So in our prior example with the BMV 080, our candidate dataset is going to be the product datasheet. So this lovely 53-page datasheet that has everything you need to know, goes way over my head, I'm not in this industry, about this sensor. And so now that we have this document as our candidate, it's still in a PDF form. And it has a lot of things like graphics and pictures and whatnot, which, as we recall, our main goal is to convert this into text. So the actual pre-processing step for getting your data ready for a knowledge base is still a decent amount of work. It's not as easy as just tossing in a bunch of documents. And for this example, one of the approaches that I might do is actually use some form of OCR or optical character recognition based extraction of the text to convert something like a PDF here into that text, which is exactly what I've done here. So in the back, I wrote a quick script that uses a language model, a vision-enabled language model, to do the conversion of a PowerPoint into just raw markdown, or essentially just styled text here. So now we can see that we've taken our candidate dataset, the document, converted it into a PDF, and then ran through another processing step to convert this into a more raw text format. So now we have this wonderfully formatted textual representation of our datasheet that includes all the good information here. What I've noted is that there's not really a one size fits all to doing your data pre-processing for your database or knowledge base that you're setting up, and it's usually somewhat customized to the specific type of data that you're working with, but is generally repeated across whatever file types you're working with. General text scraping is usually the initial approach that people try out, but more specialized approaches like what I just demonstrated can enrich or convert data into more effective formats. A little bit of experimentation needs to be done for actual production systems. And so now that we have our information and all of our information in a text format, there's still one slight issue. Language models have something that's called a context window, or essentially an upper limit to what can actually be input, or the amount that can be input into the model all at once. For those of you who might be a little bit more familiar with these systems already, you might look at this document and say, well, it's not big enough to actually hit that context window in most modern language models, so you can actually put the full document in there. And sure, but when you're working with huge data sets or maybe enterprise level systems that have tens, hundreds, thousands of documents, you're going to need a way to actually separate out those documents into bite-sized chunks that you can pass in efficiently into the language model. Which brings us to the second step. Now that we have the text, we need to do that breaking up of the text into manageable pieces, which is known more specifically as chunking. And similar to our knowledge base setup, there's also no one-size-fits-all for chunking your data into those specific pieces. Common approaches often involve splitting by common separators, like things like periods, line breaks, paragraphs, or doing it by different limits of character count or token count, or chunking your data into like 400 token each chunks, or much more advanced flows that use different algorithms. Oftentimes, it's different based on what type of data you have. Something like a data sheet here, we would want to chunk, but make sure that we do things like not split tables so that different table pieces aren't out of context or fragmented across these different chunks. This might be very different for something like a code base where you might want to do things by file or by different functions or components. And it changes generally based on what type of information or data you're actually trying to split up. So first, let's actually check how big our knowledge base is. And after running it through a tokenizer, the same one that does the conversion of tokens for things like GPT-4o, we see that it is roughly 22,000 tokens. So what I'm going to do is use a pre-made text splitter, a markdown specific text splitter, because I have all of my information in markdown format. So these pounds or hash symbols right here are different headers and correspond to things like header 1, header 2, header 3, which you might be more familiar with from things like Google Docs or Word documents. And we can use those as different indicators for splitting. And the thought process here is if we have these headers, it is likely that each of these headers are going to correspond to full, complete sections. And one of the challenges with the chunking step here is actually maintaining contextual sections. Essentially, you're going to try and balance how much information you can split into or fit into a chunk while maintaining everything that's related to that chunk. We'll talk about why this is important in the final step of the RAG pipeline, but if we actually do run this splitter, we'll see that we get out 28 total chunks from our datasheet. So we can look at one, I'll index over to chunk index 20, and you can see that this text here, which I'll just make into a scrollable thing, is the entirety of that chunk. So now what we've done is we've essentially taken our full document and split it into 28 different pieces, all of a size of roughly 1,200 tokens. I've also implemented an overlap of 400 tokens here, which is a little bit of a technique that just makes sure that the end and the beginning of these different chunks are also included along with the chunks to try and also maintain a little bit of the context both before and after what's actually been split. So, well, we've now solved our first problem of actually taking our knowledge, which might be very large, and splitting it into the manageable pieces. We've introduced another issue. Since we can't pass all context in at all times, we essentially need to find a way to find the most relevant chunks based on whatever our questions or inputs into the system are. Which brings us, finally, now that we've done all of our data pre-processing, to the retrieval part, or essentially determining what of the data or of these specific chunks are actually going to be relevant information needed to effectively and accurately answer a question or input into our system. This is going to be the step where we actually try and find what is the relevant context that is going to be used to be passed to the language model along with the query to have it generate an accurate answer. Or in other words, we need a system that can do database style retrieval of these chunks that we have, but rather than a key-based retrieval, we need it for relevancy. And so this is where the concept of embeddings or the embedding model actually play a part in the RAG ecosystem. So to add a little bit more context before we jump into embeddings, let's take our prior example of what is the maximum power consumption of the BMV 080 in continuous measurement mode. If we send that into our system, what we want to do is surface the chunk most relevant to having the answer, essentially, to actually answer that question. So what we want to do is surface what I have identified as chunk ID 6, which has that table and has that accurate information in it. So in short, when I ask this question, what I want to be passed along with this question is this table. And this table is contained in the chunk ID 6. So we need our system to be able to find what's most relevant to our question, and what should be most relevant to that question should be this chunk. So it's a little bit complicated to get to a system that actually can do relevancy or similarity-based retrieval, but the first step of this is to do what is called encoding, or essentially encode the text that we have here, either our chunk or our question, into a numerical representation known as a text embedding. And this conversion of text into numbers is done through a separate language model, not the large language models that we are familiar with things like ChatGPT, but a different kind known as a sentence transformer. And these sentence transformer models are trained to understand language and do this rich conversion of text into numbers. And the interesting part here is that the encoded numbers of the sentence are actually also meant to capture the meaning and understanding of what the text is in that passage in those numbers. So literally converting your sentence into numbers, but the numbers also represent the ideas, concepts, and meanings of the sentence. Now, how does a model actually learn to do something as abstract and esoteric as that? Well, there's a few different techniques, but one of the most popular ones that's easy to understand is through something called masked language modeling, where essentially a deep learning model is going to look at a sentence where one or multiple of the words are removed, and then it's going to predict or try to fill in the blank of that removed word with what it believes to be the most relevant or accurate word there. Now, we're able to actually verify this, and based on whether or not it gets that wrong, we're going to update the model or the internal weights and biases and neural networks and all that fun stuff behind the scenes to make it do better and more accurate predictions of language. Now, through some special neural network architectural designs using things like the transformer or attention mechanism that boosts the understanding of things like large language models, and running this over millions and millions of examples, the model itself then forms a decent understanding of language itself by doing different tasks like this. So in the end, we get a deep learning model that can take a sentence and then, based on the context of the sentence and how the different words are used in the sentence, convert those into numbers. And then all of those numbers are usually combined together through some sort of pooling operation into a final representation. So essentially your input here of the sentence turns into one long list of numbers. Now, the actual math and machine learning and deep learning behind this can get a little abstract, so let's look at this in action. If we take our question and run this through one of these encoder or sentence embedding models, we will get out here we go. A list of numbers. This is just the first 10 numbers, but we see that we get 384 numbers in this list. And these are all going to be specific dimensions. Now, intuitively, these dimensions are exactly kind of how we understand things. One-dimensional, two-dimensional, three-dimensional. Now, we don't really go past 3 dimensions in our day-to-day life unless you've really got something going on. But these try and capture different dimensionalities of the concepts across all of these different dimensions. So for more complex topics or more complex things like a sentence, there are a lot of individual nuances there. So these embedding models try to capture all of the meaning across all of these dimensions and then represent that all in numbers. Now, higher dimensional vector space, which is what something like this is called, is a little bit more difficult to intuitively understand as you and I don't live in 384 dimensions. So let's talk a little bit about why this is useful and what it's used for then. For this, I'm going to take 100 different words and concepts, run them through an embedding model, and then we're actually going to reduce those down to 3 dimensions, something that we can actually see and understand. And what we get is a graph that looks a little bit like this. And you can see that similar items conceptually are located in a similar 3-dimensional space. So different professions over here are kind of clumped together, different weather-related topics are clumped together over here, and then, kind of amusingly, all of these animals and these foods are in a similar space, even somewhat overlapping here, depending on the different labels that we actually have. And so this concept of similar concepts being located in the same kind of regions in this high dimensional space holds up as we move past 3 dimensions. So we're able to capture even more information, even more nuances about the topics in things like 384 dimensions or 768 dimensions, etc., etc. It's just a little bit hard to wrap your head around and visualize. But if we do that reduction, it looks a little bit like this, where the same concepts are similarly spaced out or similarly placed together by the model in this theoretical environment. So with the understanding of that, why is this actually useful? Because we can now compare the distance between these individual concepts in this space together to see how similar these different concepts are. So once you have this encoding or embedding of this text, it's actually relatively straightforward to find the similarity between them, and we can take a little bit of inspiration from maybe some middle school math classes with something like the distance formula, or essentially finding the distance between 2 points in a Cartesian plane or in 2 dimensions. As it turns out, the distance formula holds up across n dimensions, so not just 2 dimensions, but also you're probably familiar that you can see the distance between things in 3 dimensions, but also in 1028 dimensions. Now there's a little bit of nuance here. Modern approaches tend to use actually the difference of angles between points, but the same concept tends to follow, that we're trying to see the distance between these 2 points or 2 concepts in this high dimensional space. And it can be thought of as the distance between 2 points, very simply like this. So let's take a look at what that actually looks like. What I'm going to embed and compare is dog, cat, and Toyota Prius. Now, intuitively, I'm going to expect that dog and cat are going to be relatively similar, and these two with Toyota Prius should hopefully not be very similar. So running that through, we can see that we get the mathematical output for what this looks like. So this line represents dog, this represents cat, and this represents Toyota Prius. And we can see that dog and dog is fully similar with each other. Dog and cat is about 0.66 or 66% similar. And then dog and Toyota Prius is at 0.2199 or about 22% similar. This is in line with our expectations, but we can see how we can do this mathematically using these models plus distance calculations to see how similar these concepts actually are together. Now, this concept can be extrapolated to compare actually the documents or the specific chunks that you have, with the questions or queries or inputs that you are inputting into your RAG system, where when you send a question or a query, you can embed it and then see where that query lands, similar in this dimensional space, to the other chunks. And then the hope is that those chunks, what's most similar to that query in that dimensional space, are going to be the most relevant. And the good news for us is that those much more into databases and the theory there have created these retrieval systems in the form of vector databases that kind of automate this full process. So you can take your text, insert it into a vector database, it'll do that embedding for you, and then with your queries, you can send a query in and it'll retrieve what's most relevant. But before we actually get into showing that, let's see what our query with the candidate chunk ID 6, which we know is the chunk that we want to retrieve as most relevant, is when we run it through these models and compare the similarity. And we'll see that our question here ends up with a similarity score of 0.5966, where 1.0 is fully similar, 100%, and this one's about 60%. So just on expectations. So with that, we can actually move on to marrying it all together with the retrieval step. So putting all of our chunks into a vector database where they all go through the sentence encoding, sentence embedding model to be converted into these numbers and then stored efficiently in there. And then being able to send in our query to see what might be the top set of most relevant items. So I've already set up the database. Now, when I send in the same question with 5 results max, we shall see what actually comes out. And here we go. So the chunk that was determined most relevant is actually chunk ID 21, which we know isn't our exact candidate, but this also begs the idea of relevancy. So naturally, there's a lot of noise when doing these relevancy searches because we know that we want the power consumption, but there's also all of the text around this question that contribute to the actual embedding. And then of course the chunks have all sorts of different information, not just the exact answers in the individual chunks. So we see that not our first candidate that we know is true as the most relevant, but within our max of 5 results, we do see our golden snippet here, ID 6, come up as the second most relevant. And so that is why most of the time you're going to retrieve the top 5, top 10, top 20 or so documents, hoping that the actual answer is going to be in one of those similarity retrieved documents. It's not the most efficient, but as you've just seen, calculating something's similarity is a little bit nuanced and strange, so we don't expect kind of perfect efficiency here. But seeing that this ID6, our golden document here, comes up close to the top in second place, does give us hope. And so we know that if we were to pass our retrieval set here, all 5 of these documents, as context along with this query, that the right information is in there and should be able to be extracted by the language model to answer the question. So with our retrieval out of the way, we can put it all together into now what we understand as RAG. As a quick recap, we now have our unstructured data converted into a language model ingestible form, or the text. We've chunked that text into manageable and processable pieces, and we have now embedded all of those chunks, and they're ready for semantic similarity-based search. So now all we need to do is put it all together into something that looks a little bit like this graph. Rather than passing the user's query directly to the language model, we'll first pass it to our vector database, retrieve all of our relevant context, and then pass both the question and all of that context at once to the language model to get its response. In a little bit of pseudocode, that looks like retrieving first the context from our documents, popping that all into one single prompt, so having our context plus the question that we were asking, and sending all of that over to the language model. So without further ado, let's do just that. Running our same question through our RAG response function, we shall get the answer of 181.9 milliwatts. So with that, we've pretty much covered the entirety of a basic retrieval augmented generation pipeline, from the data identification and preparation through to actually setting up the retrieval and generation. So now you should fully understand, at least from an intuitive level, what retrieval augmented generation actually means. There's obviously a lot more complexity to this as you look into different modalities of data or optimizing the individual steps for your specific knowledge bases or for your specific application's use case. But at a core, this is how a lot of these RAG systems, which are powering the applications of tomorrow, work. So I hope you learned something interesting today. If you like the video, like the video. If you have any questions or comments, leave them in the comments down below. And if you want to see more like this, consider subscribing. If you really want to support the channel, also consider leaving a super thanks. Thank you and have a great day.